Hi everyone, welcome back. Today we're doing section 4.3, which is on derivatives of inverse trigonometric functions. So we have studied different types of inverse functions before. You know that an inverse function is created by interchanging x and y. You also know that the graph of the inverse is the reflection through the diagonal line y equals x. So we've seen that a couple of times before. We saw it with radical functions, which are the inverse of quadratics, and we also saw it with logarithmic functions, which are the inverse of exponentials. So just a mention on notation. Up until now, we've generally used this notation that I'm underlining in red when we've referred to inverse trig functions. It's kind of like a -1 exponent. And so it does have the drawback that it could be confused for an exponent, which is not ideal. So there is another notation that we'll introduce at this point, and we'll use this quite frequently going forward. So it's arcsine, arccosine, and arctangent. So it means exactly the same thing as the other notation, but it does have the advantage that it wouldn't so easily be confused with an exponent. The derivatives of the inverse functions are listed for you here at the bottom. So the derivative of arcsine is 1 over the square root of 1 minus x squared. The derivative of arccosine is -1 over the square root of 1 minus x squared. And the derivative of arctan is 1 over 1 plus x squared. Okay, let's take a look at our first example. Find the derivative of y equals arcsine of x squared. All right, so the derivative of arcsine is 1 over the square root of 1 minus x squared. Now, in this particular question, we have the arcsine of x squared. So we have x squared instead of just plain x. So we will have 1 over the square root of 1 minus x squared squared. And of course, because x squared is embedded inside the arcsine function, that means what we're dealing with here is a composite function. It's a function inside a function. So chain rule comes into effect, and we have to multiply by the derivative of that inner function. So then if we fix this up a little bit, we will have 2x in the numerator, and we will have the square root of 1 minus x to the exponent 4 in the denominator. And so there's nothing more we could do that, no more simplification. We don't have an x value that we can substitute. So that's the end of the story on that one. Example 2. A particle moves along the x-axis so that its position at any time where t is greater than or equal to 0 is x of t equals the arctan of the square root of t. What is the velocity of the particle when t equals 16? Okay, so what we have is a function describing the position of the particle. We know that velocity is the first derivative of position. So the velocity is what we're looking for. That's the same thing as the first derivative of position. So the derivative of arctan is 1 over 1 plus x squared. Now this is another case where we have a function, square root t, inside the arctan function. So we're going to have 1 over 1 plus square root t squared, and then chain rule kicks in, so we end up multiplying that by 1/2 t to the -1/2. So as we have done many times before, I'm looking at root t as t to the 1/2. So when I take the derivative, the 1/2 exponent comes out in front as a coefficient, and then we subtract 1 from the exponent, and that's how we end up with the negative 1/2. So if we work this out a bit, make it a little bit nicer, in the denominator, I'm going to have 2. I'm also going to have root t. Okay, so the 2 came from there. The root t came from what I marked in orange. And we will also have this. And of course, the square and the square root cancel each other out. So really that ends up being just 1 plus t. And the only thing we have in the numerator is just the 1. Okay, so that's our function for the velocity, 1 over 2 root t times 1 plus t. Now they asked us to actually find the velocity at a particular moment in time, and the moment in time that they gave us to work with is t equals 16. So we want to substitute 16 in place of t. And so that will give us, square root of 16 is 4, times 2 is 8, 1 plus 16 is 17. So overall, we're getting 1 over, 136. And that would be the velocity of the particle at t equals 16. There we go. So that's it for that one. And that's our final example for today.